We're going to go ahead and take a look at number 51 from section 3.7, which deals with inverse functions. So what you are asked to do in number 51 is to first find the inverse for the function that they provide you. In this case, our function f of x is going to be equal to x plus 1 over x minus 1. Okay, so the first thing that we're going to do is we will go ahead and actually work this one out. So the first thing that we want to do is take it out of that function notation. So in other words, switch out that f of x notation for y. This way you are able to clearly see your variables. So the next thing that you're going to want to do is you want to swap your x's and your y's, because again, if you noticed from what we had done in class, basically the relationship between two functions that are inverses is that the x values and y values switch places. So now I'm going to have x is equal to y plus 1 over y minus 1. But again, we're not done yet. We want to make sure that we represent this problem so that y is completely on its own, because this way that permits us to actually graph the function. So in order to do this, we're going to go ahead and I'm going to create a ratio so I can clearly see everything. And this is going to allow me to cross multiply. Okay, so this is going to give me x times y minus 1 is equal to 1 times y plus 1, or just y plus 1. And then what I'm going to do is I need to get y by itself, so I'm actually going to have to get a little bit messier with this problem. So I'm going to break down the grouping here. And that's going to give me x times y minus x is equal to y plus 1. Okay? So then what I will do here is I will start to subtract x minus y from both sides. Okay, so this is going to give me negative x is equal to y minus xy plus 1. And hopefully you're kind of seeing the rhyme to my reason here. This one is definitely messier, but what I notice is I can easily move by subtracting 1 from both sides. So move isn't really the correct way of saying it. That's, I think, more of the way that we're kind of used to seeing it. But what we're really doing is if we remove a 1 from the right-hand side, we have to remove a 1 from the left-hand side. So we're left with negative x minus 1 is equal to y minus x times y. And hopefully what you're seeing here is that each term on the right-hand side has a factor of y. So I can go ahead and factor that out, and that leaves me with 1 minus x. Okay, so I'm going to divide both sides by this 1 minus x, and that's going to give me my new inverse function. I'm going to have y is equal to negative x minus 1 over 1 minus x. So because I already know the outcome of this problem, I've worked with this problem in the past, I'm going to show you a little bit of a trick. And this is really just straight up manipulation here. What I'm going to do is I'm going to factor out a negative 1 in the numerator, and I'm going to factor out a negative 1 in the denominator. And this is what's going to happen. So I will have y is equal to negative 1, and this becomes x plus 1, all over a negative 1, and this becomes negative 1 plus x. Now I'm just going to rearrange things around, and also note that since I have a negative over a negative, these two will reduce themselves out. My numerator I'm going to leave alone and have that be x plus 1. And I'm just going to use my commutative property here in the denominator and rewrite this so that it's x minus 1. So the inverse function is actually going to be f inverse of x, if you use the notation, is equal to x plus 1 over x minus 1. Take a look at this, though. Look at the function that you started with, and look at the inverse function that you created. They're actually one and the same. So that's kind of interesting if you think about it. The function that you started out with, it's its own inverse. It's kind of cool, I think. I mean, for some of you, you might be thinking, well, we did all of that work just to show that the inverse is itself. So yes, But at the same time, it's kind of cool that you can make something so complex out of something so simple. So the last part of the question asks you to go ahead and graph both of the functions. Well, okay, well before maybe we were hemming and hawing about the fact that we went through all that work just to show that the inverse of this function is itself. Well, you only have to graph one thing. So let's go ahead and take care of that. So first off, let's note any restrictions. So for our vertical asymptote, we can't let x be equal to a positive 1. So I'm going to locate that and dot that in. The next thing we want to do is note the horizontal asymptote. Now, in this case, recall your rules. The degree of the polynomial in the numerator and the degree of the polynomial in the denominator are equal. So we're actually going to set up a ratio of the lead coefficients, which in this case is going to be 1 over 1, or just 1. So our horizontal asymptote will be here, like so. Now we just have to decide where things are going to go. We can see if we have any x or y intercepts in this case. So if we do that, let's check x-intercepts first. So we'll set our function equal to 0. We can create a ratio, cross-multiply, and we get 0 is equal to x plus 1. Subtract 1 from both sides, so we have x is equal to negative 1. So there, we're going to have an intercept there. Our y-intercept, oops, sorry, there should be one here. Our y-intercept, let's see if the one that I have is correct. Our y-intercept is going to go like so. And lucky me, I don't have to restart the video. So this becomes 1 over negative 1 or negative 1. So we do have a point at 0, negative 1. So we kind of know what's going to happen here. So we know that with rational functions, they hug the asymptotes, connect with their intercepts, and then they're going to continue to go back to hugging the asymptotes. So we have that. Now, what we might want to note is that there is a sense of symmetry along the y equals x line, so I'm just going to kind of highlight that. So as you can see, this portion of the function is symmetrical about that y equals x line. In other words, remember that that's also the value that we get if we were to compose both of these functions within themselves. But you also want to note or check, maybe using your calculator or by checking by hand, to see if the function exists elsewhere. And actually, if you were to check, it does exist here as well. Okay, so again, if you notice, if you fold your graph along that y equals x line, the points on the left-hand side of that line will overlap with the points on the right-hand side of that line. So you do have that symmetry. Okay, so there's your solution. What I have circled in red for your inverse function and what I have circled in yellow for your graph. If you have any questions or any additional comments or anything that you would like me to add on to this, please let me know. Thanks.